Yeah, so today's speaker is Claudio Pedrini, who's going to talk on the transcendental motif of the cubic fourfold.
Okay, thank you very much, and thank you to James and Roy for having me invited here. It was a very nice experience. So what I'm going to talk is, well, this is going to appear. I mean, it has been online on the Journal of Pure and Applied Algebra. So what is the idea? The idea is to try to interpret it in terms of motives, and very classical stuff about a cubic fourfold. So a cubic fourfold is just it be contained in PC over C, and it's just a very easy definition. It's just the locus of equation of degree 3. It's a hypersurface simplified, which is defined by some with the degree of f equal to 3. That's what it is. But despite of this very easy definition, the birational geometry of this gadget is a very complicated step. First of all, there is this classical conjecture that goes back to the old Italian algebraic geometry, to Fano, that the generic is not rational. And this was conjectured and never proved. In fact, there is one guy called Bolin who tried to give a proof, but was Fano himself found that it was wrong. So the point is that, so we want to try to understand this problem in terms of the motive of this guy. Why? Well, because we start look at the case of a cubic threefold. Then the irrationality of the cubic threefold it's a very famous result by Clemens and Griffith. And in fact, that result, if some of you like some history of mathematics, that result by Clemens and Griffith was a really breakthrough with respect to the old techniques of in projective algebraic geometry, because people were not able to prove. The case of threefold by Clemens and Griffith, it is not rational. By the way, all these things are unirational. So the proof of Clemens and Griffith was a really breakthrough, because it was the first example of the fact that Newton's theorem does not work in dimension 3. Because for a surface, unirationality always implies rationality. And why it was a breakthrough? Because differently what people in the classical Italian algebraic geometry tried to do was they were just considering invariants that are related with linear sections and stuff like that. But what they did, they introduced a new invariant, which is the intermediate Jacobian. And they showed, so the intermediate Jacobian, so let's call this Y, the intermediate Jacobian J2 of Y, of just calling it JY, then this is the invariant, which is just an abelian variety, just defined in terms of the cohomology, and this is the invariant that controls the rationality. And this is not rational because JY is not the Jacobian on a curve. So they found trying to find something is not rational. It's not a good. It's very hard stuff. You need an invariant controls, and they found it. So the point is, as far as now, no such an invariant exists for a cubic fourfold. But now, what I want to do, let's interpret this result by Clements and Griffiths in terms of the motive of y. And try to realize what happens in the case of a cubic fourfold. So the motive of a cubic threefold, it has a Chow-K decomposition, which is very easy. Because why? Because all the Chow groups in this case are representable. So when the variety, all the Chow groups are representable, that means, Chow groups under algebraic equivalence, whatever. If all the Chow groups are representable, then the motive is always of a real type. This lies in the subcategory generated by curves. And in this case, it's even simpler because hy, let's use the right notation, it's just 1 point plus something coming from the neuron severity plus n plus L square. This is the Lefschetz motive, okay? So everything here is trivial, but n. And n is just h1 j twisted once. For some, this might be 1 or -1, it depends what kind of, I'm using the covariant way of writing motives because this is more compatible with Podolsky construction. So that's why it's 1. But the point is that this J is isogenous to the Jacobian. And of course, so this is H1 of an abelian variety, so the motive is already a type, and everything depends on this gadget. So in this case, Clements and Griffith result say that there is an invariant that controls both the rationality and the motive. Now, the idea is, what can we say in the case of a cubic fourfold? Okay, let's go on. Oh, first of all, then there is another important result.
So your decompositions are integral motives or with rational coefficients only?
Pardon?
Decomposition is only with rational coefficients? Or
No. This is just, okay, sorry. This is in the Chow groups with rational coefficients over C. And here everything is tensor with Q, of course, because otherwise it doesn't work. Yeah. Okay, now, so Clements and Griffiths result, this result can be interpreted in a very nice way by a result of Mumford. Mumford proves that if Y is a smooth cubic threefold, then the intermediate Jacobian can be realized as a Prym variety of an étale cover of a curve. So what he shows, and I show that J2 of Y is the Prym of an étale cover. So this one is étale one cover, and I'll tell you what exactly it means. Okay, and how do you realize this? How you do? Well, let's put this L because it depends by L. And this is a very geometric and very nice construction that we can repeat in the case of a fourfold. So you take a line in Y, a general line, of course. So then you blow it up. Or if you are classical, you project. You project your object from the line. It's the same story, but we are, And then you get a vibration over P2, which is a conic vibration. Conic vibration. And then here there is a derivation curve. The curve here is the curve that parameterizes reducible conics. Okay? And then you have a double cover So this double cover is double cover with a, this is just all the lines on Y meeting F. And this is just this object, which is a quintic in P2. Remember that, because when we go to the case of fourfold, we'll find something very similar. Okay, now the point is, so what is this? This is a 2-to-1 cover. Then you have an involution, which is given just by the double cover, and the Prym variety is just the fixed part of the involution, where the involution acts as -1. Okay, now you interpret that in terms of motives. What it means? It means in terms of motives, in terms of this star, it means that you have a Prym motive, which is just constructed in the same way, and in terms of motives, you have a motive C2 pi. This is the curve. This is a projector, which is in A1 C bar cross C bar, and the diagonal is just pi plus delta C plus sigma divided by 2. Sigma is the evolution. So the Prym, this Prym corresponds to the fact that you have this is a Prym motive. So the Prym motive is just corresponds to H1 minus. What I mean the H of this C tilde, then you can suppose that it is reducible, so you can suppose to take just the normalization, where it's not, it doesn't change anything in the motive, okay? And so the motive of this curve is just 1 plus H1 plus L. And this is just the non-trivial part of the motive that depends on the Jacobian. Depends very easily on the Jacobian, because the endomorphism of H1 since B is just the endomorphism as an abelian variety of the Jacobian. This is no result. And so what he says that, so how can we interpret this result by Clements and Griffiths? We can interpret it by saying that the motive, the Prym motive, is the invariant part of the motive of H1 of a curve, but is not H1 of a curve. Because it's not the Jacobian. So it's can be realized as the invariant part of this motive under the action. Of course, it's clear that this involution acts on this decomposition. This is quite clear. So let's try to play the same game in the case. The fourfold, and we will see that playing the same game in the case of a fourfold, in fact, will give some relation with the problems of the rationality. So we just do the same construction and see what happens. So now X is B5. It's a fourfold, cubic fourfold. And we do the same construction as before. We take L, we blow it up. we get a conic fibration, just exactly. Now, here, instead, then you look S, L, of course, L is a general line. X is, of course. Now, what is SL? This is now just L prime in the Fano variety, meaning L. This is the Fano variety of lines of the cubic fourfold, which is a hyperkähler variety of dimension 4. Well, I'll get back on that. So this, now there is a result, then you can show that it has no irregularity, and it's smooth. It's smooth. In the general situation, is smooth, of course, and the genus of that thing. And PG, of SL is 5. Then here you have a completely similar situation. There is here you have a quintic surface that parameterizes reduced fibers in the conic fibration, and you can play the same game that you did before. So then you have the involution sigma, that SL mod YL mod sigma is just YL. Okay, and it's easy to see that sigma has 16 isolated singularities. Just classical thing. Then you can blow it up, so you have SL, YL. You blow up the singular points. This is a quintic surface in P3, and now what you do, you try to play the same game. So you have this sigma. Now you look at the Chow-K decomposition of this surface and see what happens by the action of sigma. Exactly like you did. The difference is here you have a surface instead of a curve. But the motive, you know that the motive, since Q is equal to 0, so it doesn't have any odd cohomology, so it doesn't have any odd summons in the decomposition. So this is just 1 plus L to the rho. The rho is the rank of the Picard, because these are plus the transcendental motive of S plus L2. It's just exactly what happens there. The difference is that you don't, this is the transcendental motive. The transcendental motive is the thing such that its cohomology is just the transcendental part of the cohomology of S. And of course, this is a mysterious part. You know, you don't know whether this is a abelian type. Should it be of abelian type, then you would have proved Bloch's conjecture if S is a surface of general type. Because the Bloch's conjecture for surfaces of general type is equivalent to show that this one has fine dimensional, but since essentially that it's the same stuff to show that it's of abelian type. So this is the, but we can play the same game as before. So the point is that this T2 is a birational invariant. This is a result that appears in an old paper by myself, Bruno Canna, and Jacob Burre. And so this is useful here because you can play the game on this without forgetting that you have some isolated points, because you blow it up, it doesn't change. So you get a map, a rational map there, so the rational map, so T2 is invariant. Then T2 of SL splits into T2 of SL plus T2 of SL minus. Here is the action plus and minus with respect to the action of sigma, exactly like we did before. This is just the T2 of the quotient and this is always different from 0 because this quintic has a genus 4. It's a quintic surface in between. It's easy to understand what is the genus, and so it cannot be 0 because otherwise, because when PG is different from 0, then the transcendental part cannot be 0 because the transcendental cohomology is not 0. Okay? So now the result. Now look at. Now it's easy to find a Chow-K decomposition for the cubic fourfold. So the Chow-K decomposition for X, the cubic fourfold, is the following. It's very easy. H of X. First of all, it's easy, but the big difference with respect to the threefold, that you don't know whether it's orbital type, because it's not true that all the Chow groups are representable. Because Chow groups in dimension 1 is not representable. Then, well, in order, let's put it this way, I'll write down the Hodge diamond so you understand what is going on with the pieces of the decomposition. Let's write it there. So H40 equal to H04 is equal to 0, H31 is equal to H13 and is equal to 1, and H22 is equal to 21. This is the Hodge diamond for the fourfold, and cubic fourfold satisfied integral Hodge conjecture. This is famous result by Poisson. Okay, so that means the decomposition I write down, you can realize with respect to the decomposition of the cohomology, and then it's just 1 plus L plus L square rho 2. Rho 2 is the rank of A2 of X, which injects into H4 of X. These are Chow groups with coefficient in Q, okay? Because everything is coefficient in Q, and so this is the dimension of this vector space. This is always injected into H4. That's because of the and then you have the mysterious part, the transcendental part, and then you have L cube and L4. So everything depends on this, and all the cohomology of this transcendental object is just the transcendental part of this cohomology. The rest is 0. So it's pretty similar. The point is that now there is a result. The theorem we proved. It's interesting because it relates with the situation of a cubic threefold. So the theorem is the following. completely analogous of what happened with the complete threefold. The transcendental motive, which is the unknown part of the motive of the complete fourfold, is completely determined by the transcendental motive of the surface, but twisted by one because of dimension. Okay? That means that the H4 of this one is just the H2 transcendental of this. Okay? Well, so now it's reasonable to try to play the same game as Clemens and Griffiths. Ask yourself if this is not all. Okay, remember that this one cannot never be the T2 of the T2, because there is a plus part here which is never zero, because the quotient has PG bigger than zero. And if a surface has PG bigger than zero, the transcendental cohomology is not true, is not zero. Okay? Now, so, question. Does there exist a surface Z such that this is completely analogous of what Clemens and Griffith proved. They proved that the thing was not rational because the H1 of the curve, twisted of course, but this is no problem, was never equal to the whole H1. The whole H1, I mean the Jacobian of the curve. Okay, so what does it mean in this case? Well, first of all, it's easy to understand that if that holds, if you go to the cohomology, you see immediately what kind of surface that is. Okay, well, you can assume that Z is smooth, otherwise you blow it up. You know, you resolve and the T2 is invariant, so you can play around with birational stuff. Okay, so if star holds, then, well, H4 of T of X has to be equal to H4 transcendental of X, then is H4 of T2 of Z twisted by 1, and this is just H2 transcendental. Of course, Z has a transcendental part in cohomology, because otherwise PG will be equal to 0, and T2 will be equal. I mean, it's okay. Now, remember what the Hodge diamond of 4x is. It's like 1. So if you just make the computation, you get, this implies that H20Z is equal to H02Z, and it is equal to 1 because of the Hodge diamond. So it means that PG of Z is equal to 1. But now something interesting comes. This is another classical law. If you have a surface, smooth surface with PG equal to 1, then the transcendental part of the cohomology, it can be realized that the transcendental part of the cohomology of a K3 surface. This implies that there exists a K3 surface such that, let's call S, such that H2 transcendental SQ is isomorphic to H2 transcendental ZQ, and so this is equal to H4 3 transcendental XQ. Oh, okay, now something interesting comes up.
What is H11?
Pardon me? H11. No, H4 transcendental. I mean, what I'm using this one, you get this one, you get this, right?
Yeah, but it's
And using this, you get, that means that PG is equal to 0, right? Then there exists a K3 surface which has such that the transcendental part is isomorphic to that.
right. So what is H11?
It's not H11, it's H4.
H22.
It's a 4.
It's 4.
There is four of the
4 transcendental X.
of the cubic.
It's not 1, 1.
I don't understand, what do you mean? I mean,
In the last equation,
yeah.
the last group, the super index is 4, not 1, 1.
Oh, I see, okay, fine. Anyway, I mean, what now becomes to become very interesting, that all the conjecture about the rationality of a cubic fourfold are related to the existence of an associated K3 surface. So we realize that the motivic approach just goes back to the same problem. So whether the cohomology of the body is the same stuff, or our K fourfold is the same cohomology of an associated K3 surface.
So because I just want to keep up. So so you mean this question for star have affirmative answer, which is coming from
If star holds, so if you can realize the motive as the associated motive of an associated surface, then surely you can realize the cohomology is associated to the cohomology of a K3 surface.
But I'm asking the transcendental part of K3 is one. So it's one something something.
You want to
one.
show what?
So what is something? It's
The K3 surface. What do you know? What the motive of a K3 surface is?
so it's a transcendental part of that.
It doesn't have out part because it doesn't have out cohomology.
Ah,
K3 surface as Q of S is equal to 0 and PG of S is equal to 1.
right.
So you don't have anything out.
I'm care about this. So you have a Picard number of K3, right? So
Right?
I want to understand
The Picard number,
20
okay.
minus that.
So
What is
H of S,
20 minus that rho.
H of S
I
is
want
1
to decide.
plus L to the rho. Rho is the rank of the Picard, of the neuron
Yeah.
severity. Plus that,
The transcendental part.
plus L2. This
Right.
is the motive. There's
Yeah.
nothing else.
So my question is, what is the 1 part of T2?
1 part.
The size of 1 part of T2.
T2, it's a transcendental part motive. It has only cohomology. It's the only cohomology is H2 transcendental.
Right, you have a Hodge number 1 something 1. So I'm asking the middle one.
Which, I mean, the odd cohomology, I mean, for the K3 surface, there is nothing odd. So the splitting is just, of course, so the H11 intersected with the integral of cohomology just gives the neural severity. What else? Hodge conjecture is true for a K3 surface. So there is nothing else but, I mean, everything is described by this, two facts. No odd cohomology, and the H11 intersected with H2 coefficient in Z is just the neural severity. Okay, now let's see the left 10 minutes. Let's relate with the conjecture about the rationality. Of course, I'm sort of, skipping. Conjecture about the rationality of a cubic fourfold, you can write a book on that because people have been working on that since, perhaps 60 or 70 years. But what I'm interested in is just, so rationality conjectures. So first of all, we have first fact. So X is always a cubic fourfold in P5. So when I want to show that the rationality conjecture are related with the existence of a K3 surface, so it's exactly what we got from the motivic point of view. Okay? So, first of all, this is the usual terminology. We divide into two different classes inside the moduli space. There is a moduli space of cubic fourfold, of course. X is special if there exists a surface sigma containing X such that the class of sigma is not homologous to the class of our upper plane section. You always okay, not homologous in H4, of course. That contains A2 of X. So that means that the dimension of A2 of X is greater or equal than 2, because you have two different classes. Okay? And very general, if dimension of A2 of X is just 1. Now, people have been working a lot to find rational examples, of course. And what it's a long story, but then in order to classify this one, what you do, you look at the intersection pairing in cohomology restricted to the lattice generated by the class of H4 and the class of this existing stuff. You restrict, okay? Take the discriminant. Of this intersection form, okay? Then it's easy. Then special. Suppose that D is bigger than 0, and also if you want D is congruent to 0 or 2 or 6, then the set of all X inside, then because C of D is an irreducible divisor in the modular space. And 4 cubic fourfolds. And then there is a result about the rationality. And the conjecture is that for special cubic fourfolds, the rationality, you can find a lot of rational examples as far as you know something about this number D. So, if D, suppose that D satisfies this condition, in general, okay, if D is not divisible, suppose that D is not divisible by 4, 9, and or a prime, but I mean, it's just a numerical condition. P congruent to 2 mod 3, Then the conjecture is that then every conjecture, every x in CD is rational and has an associated K3 surface. What does it mean? Well, it's rational, you know, that you have a K3 set whose cohomology is just given by the cohomology of X. This is a conjecture, and it has been proved for several D. Okay, so I can write down true for this. True means that people have proved that, the conjecture. D is equal to 14. And in this case, you can geometrically construct the K3 surface. This is, I'll show you what happens in the case of 14. So the known examples are 14, 26, 38, 42, 62. This is known. Then, so it's clear that what we proved with respect to the transcendental motive is strictly related to the rationality, because it just says, and of course, if so you can state a motivic conjecture about the rationality, just translating what the result. So the motivic conjecture, if a cubic fourfold is rational, then there exists a surface, a K3 surface, of course, a K3 surface S, such that K of X is isomorphic to T2 of S1. So this is interpretation. See? And relation with Kuz, I'll never write Kuznetsov, but there is something, anyway, it's Kuznetsov conjecture. Why is that important? Because this is a conjecture that relates rationality to some a property of the derived category of the cubic fourfold. So the point is that you take dB of X. This is the derived category of a bounded complexes of sheaves over X. Okay. Then you have a semi-orthogonal decomposition. You take the quotient on one. Let's put this in the right way. So it says if, so let's write down, X is rational if there exists a semi-orthogonal decomposition of the derived category, which is given by then O1 and O2. And this AX is equivalent, of course, to the SAK3 surface. So another interpretation, so this is a different interpretation of the X having an associated K3 surface in terms of the derived category. But if you look it carefully, you show that you can, this is, of course, this is very important because, you know, the derived category is related with the Mukai functor into, you know, with stuff that physicists like very much. But anyway, what the point is, then when you say that the derived category has an orthogonal part, which is just the equivalent to the derived category of K3 surface, you are not saying anything else than an information about the motive, because this S is not unique. Because if DBS1 is isomorphic or equivalent to DBS2, well, it's well known that the equivalence of the derived category does not imply that the thing is isomorphic. But that does imply in the case of a K3 surface that they have the same motive. This was Orloff conjecture that this implies the H of S1 is the isomorphic H of S2. So it coincides with the result above. We cannot expect anything else than having something that involves the motive of the surface, of the K3 surface. You cannot expect to have a unique K3 surface because it's wrong. You have example with you know, a billion varieties and the dual. And well, this was a conjecture by Orloff that was proved in some cases by student of mine, and then it has been extended to any case by Ubrecht. Okay. In general, is a result of Ubrecht. So this is now. Now it makes sense. I mean, what we are doing, we found a strict relation with our property on the so just another question, another thing. Of course, and people should expect. So there are a lot of rational K3 cubic surfaces inside this irreducible divisors. Okay, but the question is, what happens if it's not special? This is very general. The conjecture is that it should be not rational. And in fact, of course, we are not able to prove that otherwise. But it's clear from what we did that if the dimension of A2 of X is equal to 1, there is no associated K3. Why? Just make a computation on the odd diamond. Because if it is very general, then rho 2 of X is equal to 1, but then it means, then you have the dimension of H, because if there is a surface T2 of K3 such that this is isomorphic to T of X, then computing could, then you have that the dimension of H2 transcendental SQ should be equal to the dimension of H4 transcendental of XQ, but then that is impossible, because this one, since the A2 of X is equal to 1, it's just by looking at the Hodge diamond, this dimension is 23 minus 1. H04 plus HZ plus, because H3 1. But this one, while the dimension of H2 transcendental SQ is less or equal to 21.
That's what I exactly asked.
Oh, I don't know. So
H20, H02 both are 1. And the only difference is the middle piece, the 1.
yes.
So certainly your computation is 21, so it's larger than 20.
Okay.
That's
So I mean,
that's
this is
what-
so it cannot happen
Yeah.
because 22 is bigger
They
than
are
21.
confused, so you said.
Okay, I'm sorry. Anyway, now it's clear. Okay.
Yeah.
The Hodge this one is since the then this is cannot exceed
That should
21.
be
Because
smaller.
B2 is 22.
Right. The middle one, the maxima, the transcendental part is maxima 19, 19, right?
What?
19.
Branded is what?
You have a polarization. The Hodge number is 121, right? And you have the 20. In the 20, you have a 1 is polarization. So maximum possibility is 19.
Yeah, but I mean,
It's 90.
I mean, I know what you mean, but this is not, here is much simpler.
Yeah, that's what I asked.
Okay,
That is-
so now let's look at an example. Let's see an example to understand what's going on.
And before we erase all this, so this result of Holbrecht is
Pardon
conjecture
me?
of all of this is for K3 surfaces. Yeah.
For K3,
I mean,
no.
Yeah, this is K3.
For K3. No, all of conjecture is more general, but as far as I know, it has been proved in the general case. First, it was proved by myself and the student by myself in the case where this one has finite dimensional motive. Then it has been extended by Holbrecht to any K3. But I mean, what is important that it tells you that no matter what kind of conjecture you're looking at, you always come down to a question of the associated motive.
When you say all of conjectures more generally, so for which kind of varieties would you expect this to be true?
I think the all those conjecture. I don't remember the originally was only for K3 or for any surface. Okay, but for sure, the point is, no, you're right. I mean, even if you take any surface, then of course you have the problem that you cannot even understand what the statement is because you don't know exactly what the Chow. I mean, you should know what the transcendental part is. Yeah, the point is that in this case it's very easy because for a K3 surface, I mean, essentially the T2 is irreducible. So okay. Anyway, now let's see an example to see how you really put your hands on the associated K3 surface, because that's why here it means like it's something very abstract. So just take the easiest example where you know that the irreducible divisor is made up of all rational. Of course, in that divisor, the general thing should be rational. Of course, if you take a specific cubic surface, then you might very easily prove that it's rational. Of course, for instance, if you take an X containing two planes, then the rationality is very easy to be proved. You take the two planes. This is just an exercise in undergraduate geometry. You take one point here. You take points, and you take all the line connecting two points. Then since it is a cubic, then there is a third. So you can associate. The two planes is rational. This is a very easy example. Take all the points in the two. There are two planes, right? Pi 1, pi 2, and another pi 2. Then this is the third intersection because it's a cubic. So you have P2 times P2 minus S rational thing into X. This is a P4, of course. Where S is the what? What is the determinancy locus of this map? The locus where these lines lie in X. Okay, so you don't get a third intersection because all the line lies in X. And what is this? The S is the law is equal to. So this example tells you how easy it is in this case. Okay, the S is the surface generated by all lines connecting two points in the different planes. Suppose the planes are skew, of course. To skew by when the line for all L line on X. So the arithmetic section does not exist, so the map is not determinate. Then in order to make a birational, you just blow up. And the indeterminacy laws. Okay. This is a very now then look at a more complicated case, but so let's take the case. Where was that written? I wrote it somewhere. Okay. Every cubic fourfold such that the discriminant is 14 is rational, has been proved. Okay, now I'm asking you, I want to understand, well, if I believe in the conjecture, then I can put my hands on some K3 surface. You know, geometrically constructed. Always, I mean, maybe I'm just going to repeat that. I mean, all those theorems are kind of abstract stuff. No, there is some tests to cosmology, but in geometry, I really want to put my hands on this. So here it's very easy, because X, as I told you, all these cases are cases of spatial cubic fourfold. It means that they contain a spatial surfaces which is not homologous to diagonal section. So the geometry is richer, of course. In this case, X contains a smooth quartic normal swell, which is of course a rational surface, okay? And the associated K3 surface is a K3. I mean, I'm always remember, you were right. I mean, all these K3 are polarized. So I mean, that they have a genius that depends on the L square, on the the square of the line bundle that gives the polarization. It's a K3 of genus K. That means it is polarized by some L, such that L squared is 2G minus 2. That's what I mean by the genus of a K3 surface. The polarization such that GZ. And parametrizing K3 surface S, parametrizing smooth or all the smooth quartic normal flows. And so, same cases you can try. You know, you can play the same game with different cases. Once you have, you know, for instance, once you have all these examples of spatial are essentially. You can understand the geometry very easily, but they usually they contain a rational surface, like in this case, a plane, could be an elliptic regular surface or whatever. So, for instance, if this is an elliptic glued surface, then here you get a del pezzo vibration. So the geometry in this case is controlled, but it's the pezzo vibration of the oh, sorry. The vibration in the pezzo surfaces with genus 6. And that's so, for instance, just I mean, just to understand how the geometry goes on. if you have like this elliptic real surface, you can have, there you had an equartic normal scroll, or you can have a plane, all rational stuff. Then you play this game and try to understand what the vibration you get about. And of course, it depends. The general one will be, so this is very, geometric. If you look at something like this, it means you are looking at some special cubic fourfold with some rational class, which is not homologous to the algebra section. Then you're asking when it's rational. Well, of course, if you have a section here, then it's rational. In general, it does not have a section. So when you are inside this irreducible divisor, you have to look whether, and you look at this the thing. For instance, it depends on vibration. If it has a section, should be rational. It's clearly rational. Conjecturally, if it does not have a section, should not be rational because this is a case where D is 18. So it's conjecturally should be not rational. So the geometry is very clear. I mean, it's, of course, inside this irreducible divisor, there are specific things which might be rational because they have a rational section. But the general one should be not rational. And that's the end of the story because nobody was able to find an example of non-rational cubic fourfold, apart from that guy Morin who tried to prove it, but gave the wrong proof. Thanks.
A very late question, so I'm not so strong in geometry. So you discussed fourfolds, in this Fano conjecture. And then you mentioned, okay, the classical case of threefolds. So if you go to higher cubic d-folds,
well, if you go,
that becomes easy then?
Okay, yes,
I would guess
yes,
so.
yes. There are
So
examples.
this is really the borderline case.
Yes, there are examples of where they can prove irrationality for hypersurface, cubic hypersurface in higher space, with higher dimension. But in that case, I was not mentioning that because this is not really, you cannot interpret it in terms of motive, but there is another way of, as I told you, people spend a lot of time to try to get some invariance. The way you're talking, the thing you're talking about, whose results are proven by considering what happens to the Chow knot of X is isomorphic to Z. That's known. It's a unirational stuff. So it's clear that the Chow group of zero cycles on a cubic fourfold is because 2 points are always connected by rational curve. Now, then you can extend the base field and look at this. This is sort of, Bloch's Srinivas argument for the group of zero cycles. If the conjecture is that if this one still remains left, then the thing is rational. In some cases. That's another way of proving rationality, and that works for higher dimensional stuff. In some cases, there are results by Voisin and Colliot-Elette. The point is that this thing doesn't mean a damn thing over in terms of motives, because when you take Q, then the thing splits, and so the point is you want this. Then of course this gives decomposition of the diagonal over K of X. And of course this group is completely different from that of a priori. Okay? And this is the way that people prove some result about the rationality for things of higher dimension.
Okay, so that's the technique, and then what's the result? So if I look at
if you look
d-dimensional cubics for d larger than 4,
there are examples of where they can prove their irrationality because they can prove the fact that this one is not true.
So there are examples where things are not rational.
Yes.
And generically, it's obviously
Yes,
rational.
yes. But not for a cubic fourfold.
Yeah, that I understand.
And then people have been doing a lot, like they found vibrations where some fiber are rational of this higher stuff, higher dimension, where some fiber are rational and some other are not. You have, you essentially most of the results in this direction. So the conjecture, is this is rational. And the best results are the conjecture is given by Voisin, and then there are results by Collion, Telen, and Pilushka, and other people. But nothing for cubic fourfold. The equations stay there.
Are there known cases where, are there cases where Kuznetsov's conjecture is known to hold, where that semi-orthogonal decomposition doesn't have some obvious lifting to some motivic decomposition?
You mean?
Right, where you can say, okay, the derived category of the cubic fourfold has this K3 category in it, which is the derived category of some K3 surface.
Right.
But there's not some obvious way to see that K3 surface motivic.
Sure,
So
sure.
there are known examples.
Yeah, well, the point is, yes and no, because the point is that it has been proved that the Kuznetsov conjecture, whatever that
Right.
is exactly equivalent to in the case of special cubic fourfold, it's equivalent to the conjecture about that number D.
Mhm.
So, in those example, if you produce a concrete example, like I say for D14 or D18, then you can understand what the surface is.
Right.
But a priori, in Kuznetsov conjecture, that in fact, as I told you, you cannot expect to have the explicit, because the only thing that it does tell you that you have something which has the same motive. So it means that you have something that has the same cohomology. But forget it. The point is the advantage of the approach about the irreducible divisor CT that has been essentially by Hassett is that usually when you have a specific surface that that gives you the discriminant, then you can blowing it up. Then you have some rich geometry, and you can understand what the K3 surface is.
Any other question?